Welcome back. This will be a short video lecture on section 3.6 of the text, Linear Transformations. Now I've divided this section up into 5 subsections: linear transformations, special transformations in the plane, new linear transformations from old, inverses of linear transformations, and associativity. I'm going to cover the first 2 subsections in this lecture in part A, and I will save the last 3 for a part B. So let's begin with linear transformations. Now, a transformation is just a fancy word for a function that takes Rn into Rm. In this example, we're going to look at a transformation from R2 into R2. In this transformation, t is defined as follows. T is going to take a vector with components x and y, and it's going to return a vector with components 2x minus 3y and 4x plus y. Now, in each case, for the given vector v, we're going to evaluate t of v, and we're going to draw v and t of v on separate copies of R2. And we're going to do this for the vectors v with components 2 and 1 and 3 and 0. So join me at the document camera to work through the details of this problem. All right, welcome to the document camera. Let's take a look at this problem. We've got our transformation t taking a vector in R2 and returning a vector in R2, and we simply want to know what is this transformation t going to do to this vector with components 2 and 1 and to this vector with components 3 and 0. And it's actually quite simple. All we have to do is apply the rule. We take the components x and y and feed them in according to these formulas. And so we'll have 2 times x, so 2 times 2, minus 3 times 1. That'll give me the first component of the output vector. And then we'll have 4 times 2 plus 1. That'll be the second component of the output vector. So the output vector is simply going to be 4 minus 3, or 1, and 8 plus 1, or 9. So the vector 2, 1 goes into the function, and the output vector is 1, 9. Now let's do this for 3, 0. We'll have 2 times 3 minus 3 times 0. And in the second component, 4 times 3 plus 0. And this will give us an output of 6 and 12. So the input vector 3, 0 is getting transformed into the output vector 6, 12. Now, let's look at how we can visualize this. There's a couple of different things we can do in this case. Because this is a transformation from R2 into R2, there will be a couple of different presentations that we can have. So one way to picture this, let me show you method number 1. And this is to imagine we've got a representation of R2 here. So this is the plane. And then this will be where we visualize our input vector. And then we'll have another version of R2 here. And here's where we'll represent our output vector. So one way to think about this is we have our input vectors on the left and our output vectors represented on the right. And our transformation t is mapping these vectors into these vectors. So, for example, for the transformation t that we're studying, we know that the input vector 2, 1 gets transformed into the output vector 1, 9. So we'll think of this as the input, and this is the corresponding output. Now, because this is a transformation from R2 into R2, there is a second way that this is often visualized, and this is just by thinking of the input and the output vector being graphed simultaneously in the plane. But in this case, I might use one color for the input vector and a second color for the output vector. So if I want to think of this as a transformation within the plane, I can think of my input vector 2, 1 being mapped to my output vector 1, 9. So I can kind of imagine this vector kind of being stretched and scaled and moved from this position to this position. Okay, so this is an effective way of handling, let's say, representations of transformations that map the plane back into itself. And we'll be seeing lots of examples of this later, so we'll have this kind of second representation available to us. All right, so that's the conclusion for this problem. Let's head back to the class notes and continue. We now come to the very important definition of a linear transformation. So a transformation t from Rn into Rm is called a linear transformation if t of a sum of vectors u and v is the same as the sum of the vectors t of u and t of v. And property 2, t of a scalar multiple of the vector v is the same as that same scalar multiple times the vector t of v. Now, I like to think of this visually. When I look at this first rule, it looks like I can basically distribute this transformation t over that vector sum. So t of u plus v is the same as t of u plus t of v. And when I look at this second one, I visualize it as being able to pull the scalar through the transformation. So t of c times v is the same as c times t of v. So these are the two hallmark properties of a linear transformation. So let's work through a couple of examples and get comfortable with the idea of a linear transformation. For our first problem, let's show that the transformation defined as follows is a linear transformation from R2 into R3. So join me at the document camera to work out the details to this problem. All right, welcome to the document camera. Our goal is to show that this transformation from R2 into R3 is a linear transformation. So what we're going to need to do is to set up some generic vectors. So I'm going to say u is the vector, let's say with components x1 and y1. And let's let v be a vector with, let's say, generic components x2 and y2. So what we have to show, and let's let c be a scalar. All right, so what we have to show is that when I apply t to u plus v, that's the same thing that I would get as if I applied t to u, applied t to v, and then added those results together. All right, so I have to kind of show that this transformation distributes over that vector addition. All right, so what I need to do is look at what happens when I add u and v together. So t of u plus v is the same as t applied to the vector with components x1 plus x2 and y1 plus y2. That's the sum of u1 and v, u and v. Now when I apply this transformation to this vector sum, I'm going to get 2 times the first component, x1 plus x2, minus 3 times the second component, and then I'll have 4 times the first component, plus the second component, and then finally I'll have 3 times the first component, plus the second component. So I'm just simply applying the transformation rule to this vector with first component x1 plus x2 and second component y1 plus y2. Now what I'm going to do, and I'll just do this, I'll do a couple of steps here. I'm going to distribute the 2's and the 4's and the 3's, and I'm going to collect terms that are like each other. So I'm going to collect the terms with subscripts 1 together and terms with subscripts 2 together. So I can easily rewrite this as, it'll be 2x1 minus 3y1 plus 2x2 minus 3y2. So that's another way of rewriting this first component. I can do likewise here. I'll have 4x1 plus y1 plus 4x2 plus y2. And then finally, likewise down here in the third component, 3x1 plus y1 plus 3x2 plus y2. Now I can see that this is a sum of 2 vectors. I can write this as a sum of the vectors 2x1 minus 3y1, 4x1 plus y1, 3x1 plus y1, plus 2x2 minus 3y2, 4x2 plus y2, and then finally 3x2 plus y2. And then if I stare at this, I'll realize that this is nothing more than the transformation rule applied to the vectors, with the vector with the components x1 and y1. So this is just t of x1, y1, and that's t of x2, y2, and that's just t of u plus t of v. So we've shown that the transformation t applied to the sum u plus v is t of u plus t of v. And that's the first part of showing that t is a linear transformation. The second thing we need to do is to show that if I scale, let's say, u by c and apply the transformation to that, that's the same thing as applying the scalar c to t of u. So let's check that. This is like part 2. So I'm going to apply t to the vector c times u. Now, we know what c times u is going to be. C times u is just going to scale each of these components by a factor of c. So t applied to c of u is the same thing as t applied to cx1, cy1. And now I'm going to apply the transformation rule to this vector. So I've simply taken my transformation rule and I've applied it to a vector with this first component and this second component. Now, one thing I notice is that every one of these components has a c that I can factor out. I can factor that c out of every one of these components. So this is the same thing as c times 2x1 minus 3y1, c times 4x1 plus y1, and c times 3x1 plus y1. My last move is to realize that this is just scaling this vector by c. So this can be written as c times 2x1 minus 3y1, 4x1 plus y1, 3x1 plus y1. And finally, if I stare at this, I'll realize that that is just the rule, or the transformation t applied to the vector x1, y1. So this is just c times t applied to x1, y1. And that's just c applied to u, or t applied to u. Okay, so t applied to cu is the same thing as c times t of u. And so that's part 2 of showing that the transformation t is linear. So we've got t distributing over the vector addition, and we've got t obeying this scaling law. Putting those two together, we see that this transformation t is in fact a linear transformation. For this next problem, we want to show that projection gives us a natural linear transformation from Rn to Rn. So in this problem, let V be a vector in Rn. We want to show that the transformation defined by T of U is the projection of U onto V is a linear transformation from Rn to Rn. So join me at the document camera. Let's work out the details to this problem. All right, welcome to the document camera. We need to show that this transformation, the projection of U onto V, is a linear transformation. So we have to show our two properties. We need to show that T, in a sense, distributes over vector addition, and we need to show that T we can pull the scalar through the transformation t. So those are our two defining properties of a linear transformation. Now, the thing that helps us here, the thing that allows us to make any progress on this problem is that we know how to project u onto v. We simply have to compute u dot v, divide that by v dot v, and that's a scalar which is going to multiply the vector v. So that's how we form the projection of u onto v. So we have this kind of simple rule for calculating t of u. Now we just need to show that this satisfies the properties of a linear transformation. So let's take vectors u1 and u2, arbitrary vectors. Let's add them together, and then let's apply the transformation t. We want to show that this is the same thing as t of u plus t of u1 plus t of u2. All right. Now, according to our formula, we just take our vector u1 plus u2, we dot that with v, we divide by v dot v, and that's a scalar that's going to multiply the vector v. Now, we know from the properties of the dot product that we can distribute our dot product across the sum. And so I can write this numerator as u1 dot v, u2 dot v. And I can add those together. Now, they have the same denominator, v dot v, so I can just represent that as v dot v dividing the first term and v dot v dividing the second term. Okay, so then a couple of steps there. Now my vector can be distributed across the sum of scalars, and so this can be written as u1 dot v divided by v dot v times v plus u2 dot v divided by v dot v times v. And when I stare at this, I'll realize that this is just the projection of u1 onto v, and this is the projection of u2 onto v. So this is t applied to u1 plus t applied to u2. So effectively, we've shown that this transformation distributes across that sum of vectors, and so t of u1 plus u2 is equal to t of u1 plus t of u2. All right, now let's let c be a scalar, and let's say we're scaling a vector u by c. We want to apply t to that scalar multiple of the vector u. Now, what does t do to the vector c times u? It's going to take c times u. It's going to dot that against v, or dot that with v, if you will, divided by v dot v. That's going to be another scalar that's multiplying our vector v. Now, one thing we know about dot products, though, is that I can take the dot product of cu with v by first taking the dot product of u with v and then scaling. So this numerator is equivalent to c times u dot v divided by v dot v times the vector v. Now I can think of this as the scalar c multiplying the scalar u dot v divided by v dot v, and that double scalar multiplying v. And so I can render this as c times u dot v divided by v dot v times v. Now this part of it is the projection of u onto the vector v, so this is just t of u, and then we're saying that this is therefore equivalent to c times t of u. And that shows that t satisfies that scaling law. So together, these two show us that t is in fact a linear transformation. So we've shown that a projection of a vector u onto another vector v is always going to provide us with a linear transformation. Okay, let's head back to the class notes. Now, Theorem 3.30 says something very important. It says, once I have a matrix, I can always define a linear transformation associated with that matrix. Let's look at the details. Let A be an M by N matrix. The matrix transformation T sub A maps Rn into Rm, and it's defined by this action. T sub A applied to a vector x is simply A times x. And what the theorem asserts is that this is always going to produce a linear transformation. Now let's make sure we understand what's going on the right-hand side here. Remember that A is an m times n matrix, and X is a vector in Rn. In this representation, we're thinking of X as a matrix itself with n rows in a single column. So this matrix multiplication makes sense, and it's going to return a value in Rm. So our task is to show that this matrix multiplication, this action, always produces a linear transformation. All right, welcome to the document camera. Let's look at the proof of theorem 3.30. We want to show that this always defines a linear transformation. So let's begin by taking a pair of vectors, let's say x and y, and we're going to add them together, and we're going to apply our transformation to that sum. Now, according to our rule, we're just going to take the matrix A and multiply it by the vector sum x plus y. But by our properties of matrix multiplication, we know that we can distribute matrix multiplication over vector addition. So this is simply A times x plus A times y. And if we stare at this, this is the same thing as the transformation T of A applied to x plus T of A applied to y. And that shows that effectively the transformation distributes across vector addition. T of A applied to x plus y is the same as T of A at x plus T of A at y. So that's step one. Now, let's imagine taking a vector x, scaling it by a factor of c. Let's see what happens when we apply our transformation to c times x. So according to our rule, that's just going to be the matrix A multiplying the vector or the matrix c times x. But we know from properties of matrix multiplication that that scalar can be thought of as sitting out front of the matrix multiplication A times x. And looked at it this way, this is just c times T of A applied to x. So this satisfies the scaling law for a linear transformation. Effectively, I can pull the scalar through, and so T of A applied to C of x is the same as C times T of A of x. And so this shows us that this kind of transformation, a transformation that's defined through matrix multiplication, is always going to provide us with a linear transformation. And this is a very important class of linear transformations, transformations that come about through matrix multiplication. Let's head back to the class notes and continue. When we first encountered the definition of a linear transformation, we saw that there were two things to check. We had to show that our transformation acted in a certain way with respect to vector sums and in a certain way with respect to vector scaling. Now, it turns out we can check both of these conditions at the same time. We can check them with one condition. So let T map Rn into Rm. T is a linear transformation provided that T applied to C1 times V1 plus C2 times V2 is equal to C1 T of V1 plus C2 T of V2. And this has to be true for all choices of vectors V1 and V2 in Rn and all choices of scalars C1 and C2. Now, when T is a linear transformation, we can look at this defining property through a geometric lens. So let's take a look at this. On this left-hand side, C1v1 plus C2v2 is nothing more than a linear combination of the vectors v1 and v2. And so this left-hand side is just applying the transformation T to a linear combination of v1 and v2. Now let's look at the right-hand side. What is this? T of v1 is the output of the vector v1, and T of v2 is just the output of the vector v2. And what do we have here on the right-hand side is a linear combination of the output vectors T of v1 and T of v2 using exactly the same scalings C1 and C2. So T takes a linear combination in, and it produces a linear combination of those output vectors using exactly the same scalars, in this case C1 and C2. Now, we can extend this rule to sums of more terms, and it's not hard to show using a little induction argument that we can extend this rule to sums of 3 or 4 or 5 vectors at a time. So here's an extension of this rule. If I take the linear combination C1V1, C2V2, and C3V3, and I apply my transformation T to it, it should be, if T is a linear transformation, it should produce C1 times T of V1 plus C2 times T of V2 plus C3 times T of V3. In other words, T applied to a linear combination, in this case of 3 vectors, will produce a linear combination of the 3 output vectors using exactly the same scalars, in this case C1, C2, and C3. Now, this is an incredibly important property of linear transformations, and in the next couple of problems, I want to show you how we can use this property to our great advantage. In this problem, let T take R3 into R4 be a linear transformation. Now, suppose we know how T acts on E1, E2, and E3. So we know the output vectors for the inputs E1, E2, and E3. Let's find T applied to the vector with components 2, -3, and 4. And let's find an expression for T acting on a generic vector with components X, Y, and Z. So join me at the document camera for the solution to this problem. All right, welcome to the document camera. We've got a transformation T from R3 into R4. It's known to be a linear transformation, and we know 3 things about this transformation. We know what happens when I apply T to E1, when I apply T to E2, and what happens when I apply T to E3. We get these 3 output vectors. Now, I claim that that's all the information we need to know. Now we can calculate T applied to, for example, this vector with components 2, -3, and 4. And the idea is to rewrite this vector as a linear combination of E1, E2, and E3, and then apply our linear transformation rule to that. So we can think of this vector as 2 times E1 plus a -3 times E2 plus 4 times E3. Now, because T is a linear transformation, I can basically distribute T across the vector sum and use my scaling law to write this as 2 times T of E1 plus -3 times T of E2 plus 4 times T of E3. But I have explicit output vectors for T of E1, T of E2, and T of E3. So I can write this as 2 times 1, 2, 0, -1, -3 times 3, 4, -2, and 0, and 4 times 5, 1, -2, 3. Now, from here, I could simply compute the output vector that results. I could simply scale and add the vectors together and get the result. But I want to show you something a little more sophisticated that's actually pointing us in a very fruitful direction. Anytime I have a linear combination like this, I can always represent it as a matrix whose columns are the given vectors times a column vector whose components I get by looking at these scalars. So in other words, I can render this as 1, 2, 0, -1, 3, 4, -2, 0, 5, 1, -2, 3. So I can take that matrix that I get by inserting these as columns times the vector 2, -3, 4. Okay, so that's always available to me. I can always write this linear combination as a product of a matrix against a vector. Now, when you do that, you finally get the answer 13, -4, -2, 10. So there's the output vector. But this ends up being a winning idea. So if I want to calculate t at 2, -3, 4, I can simply take that as a column and multiply it by this matrix. The matrix is obtained by looking at these output vectors for t of e1, t of e2, and t of e3 and inserting them as the columns of a matrix. So this calculation can be done through matrix multiplication. All right? Now, let's think about this in problem 2 in general. There was nothing special about 2, -3, and 4. I can kind of follow the same strategy if I wanted to compute t at generic x, y, and z. I could simply write it as t at x times e1, y times e2, and z times e3. I can use my linearity properties of t to write this as x t of e1, y t of e2, and z t of e3. And then following exactly the same strategy as before, I can insert the explicit columns for t of e1, t of e2, and t of e3. They're going to be the same columns that I'm seeing here, and I'll have x, y, and z in place of the 2, the -3, and the 4. So following exactly the same strategy, I'll be able to express this as the matrix 1, 2, 0, -1, 3, 4, -2, 0, 5, 1, -2, 3 times the vector x, y, and z. So if I wanted to compute t at a generic vector x, y, z, I could simply take the matrix times that column vector x, y, z, and that would tell me how t acts on that vector. Okay, so that's the conclusion to this problem, and there's underlying this problem is a very, very nice idea, which we'll explore in our next problem. Let T map R2 into R2 be defined by this relationship. Now, earlier we showed that T is a linear transformation. Now what we want to do is show that T can be represented by a matrix. That is, applying T to the vector xy is equivalent to taking some matrix and multiplying it by the column vector or the column matrix with components x and y. So let's go to the document camera and show how this linear transformation T can be represented by matrix multiplication. All right, welcome to the document camera. We've got our transformation T. It's taking R2 into R2. We know that this is a linear transformation because we studied this one in detail earlier. All we want to do is show that we can represent this transformation through matrix multiplication. There's a matrix that represents this transformation. All right, now borrowing an idea or an insight from the previous problem, let's calculate T at E1 and at E2 and see what the outputs for E1 and E2 are. So let's say I want to calculate T at E1. That's, of course, T at the vector 1, 0. Plugging in, we'll get 2 times 1 minus 3 times 0. 4 times 1 plus 0. And so this is giving us the output vector 2 and 4. Likewise, T at E2 is T applied to 0, 1. And that's going to be 2 times 0 minus 3 times 1, 4 times 0 plus 1. And so that's going to be the vector -3, 1. All right. Now I claim that that's all the information we need because of the linearity of T. Everything is determined, in a sense, by what T does to E1 and E2. Let's kind of remember how this progression works. Suppose I wanted to calculate T now at a generic vector with components x and y. All right. What I would do is I would write xy as a linear combination of E1 and E2. I'd say it's x E1 plus y E2. And now I can use my linearity property and write this as xt E1 plus yt E2. Now we know what t does to E1 and E2. I have those explicit output vectors for t of, I have explicit representations for t of E1 and t of E2, so I can insert them here. And now I can see that this is a linear combination of these columns, and so I can represent this linear combination as a matrix with these columns times a column vector consisting of x and y. So this can be rendered as 2, 4, negative 3, 1 times the matrix or column vector xy. So if I want to calculate t at xy, I simply have to take my vector xy, treat it as a column, and multiply it by this 2 by 2 matrix. And so the action of t is determined by this matrix here. And again, let's just remind ourselves, where are these columns coming from? This is t of E1 and this is t of E2. So what I want to do is take the basic principle that we've been studying here in these last couple of examples and apply it and formulate a general rule. Let's head back to the class notes and do that. Now the results of our previous two problems have led us to theorem 3.31. Let T map Rn into Rm be a linear transformation. Then T is a matrix transformation. More specifically, T can be thought of as the transformation induced by a matrix A, where A is the matrix obtained by making T applied to E1 the first column of the matrix A, T applied to E2 the second column of the matrix A, on out to T applied to En the nth column of the matrix A. So once I know T applied to E1, T applied to E2, on out to T applied to En, I can form this matrix A, and the action of T is in fact given by multiplication against this matrix A. Now let me show you how we can put theorem 3.31 to great use in studying some special transformations in the plane. Now for our first example, I want to study reflections through the x and y axis. So let T1 be the transformation that takes the input vector xy and returns x negative y. And let T2 be the transformation that takes the input vector xy and returns the output vector negative xy. So T1 is a reflection through the x-axis, and T2 is a reflection through the y-axis. What I want us to do is find matrix representations for T1 and T2. So let's go to the document camera and work out the matrices that represent T1 and T2. All right, welcome to the document camera. In this problem, we're going to work out the matrix representations for the transformations T1 and T2. Now T1 is a reflection through the x-axis. The input vector xy is being transformed into the output vector x comma negative y. So that simply corresponds to a reflection of the input vector through the x-axis. Likewise, T2 is a reflection of the input vector through the y-axis. xy is being transformed into negative xy, a reflection through, in this case, the y-axis. Now what we want to do is find the matrix that represents T1 and the matrix that represents T2. So let's first calculate T1 at E1. So T1 applied to E1 is what I get when I apply T1, of course, to the vector with components 1 and 0. And if we simply follow our rule, that's going to return 1 and 0. Okay? Now T1 at E2 is going to be T1 applied to 0, 1. And according to our rule, we simply have to change the sign of the second component. So this will be 0, negative 1. So the matrix that represents T1, we'll call it A1, is going to be the matrix with these columns. Okay, so we can say in this notation T1 is represented by T of the matrix A1. All right, so I can represent this action or reflection through the x-axis by simply taking my input vector and multiplying by this matrix A1. Now let's do the same for T2. T2 at E1 is T2 applied to 1, 0, which is going to be what I get by applying the rule T2. So I have to change the sign of the first component and substitute in the second component. All right, so that's T2 applied to E1. Now let's check T2 applied to E2. Now, according to my rule for T2, I change the sign of the first component and leave the second component unchanged. Well, the changing the sign of 0 leaves 0, and I put in the second component. And so that's T2 applied to E2. So the matrix that represents T2, I'll call it A2, is going to have columns -1, 0, and 0, 1. All right, so in the notation we could say that T2 is the transformation corresponding to the matrix A2. So if I want to calculate a reflection through a y-axis, I can take my vector and simply multiply by this matrix, and that will have the effect of reflecting it through the y-axis. Okay, so that's how we can calculate the matrices associated with these reflection transformations. Let's head back to the class notes. So in this problem, we're going to study rotation on the plane. Let r sub theta be the transformation that rotates a vector counterclockwise through an angle theta. In the picture here, we can see the action of rotation counterclockwise by 30 degrees. So our input vector is u, our output vector is r of u, and you can see that what we've done is we've rotated u through 30 degrees in the plane counterclockwise. Now what we want to show is that this transformation, r sub theta, can be represented by the 2x2 matrix with entries cosine of theta, minus sine of theta, sine of theta, and cosine of theta. Let's go to the document camera and work out the details for this transformation matrix. All right, welcome to the document camera. We're going to work out the matrix associated with a rotation transformation where the rotation is a counterclockwise rotation through an angle of theta. And in this picture, I've got the unit circle drawn, and I'm picturing E1 and E2 with their tips on the unit circle. The effect of applying this counterclockwise rotation through this angle theta is going to be to produce from E1, we're going to get this output vector r applied to E1. And for E2, we're going to get this output vector r applied to E2. And in order to get our matrix associated with this transformation r, I simply need to work out the components of r of E1 and the components of r of E2. Now that's the same as finding the coordinates of this point on the unit circle and the coordinates of that point on the unit circle. Now, just from basic understandings of the unit circle, we know that the coordinates of this point are going to be cosine of theta and sine of theta. All right, so r of E1 is going to be the vector with components cosine of theta and sine of theta. All right, so that one's relatively easy because we can just use our basic knowledge of the unit circle to get that coordinate. Now, this one's a little more challenging because we need to know, we need to understand that this point here has a terminal angle that's theta plus pi over 2. So the coordinates of this point are, in fact, let me do the work here. I can just indicate that the coordinates of this point are going to correspond to cosine at pi over 2 plus theta and sine of pi over 2 plus theta. So those are going to be the coordinates of that point. Now, we need to use our addition formulas for cosine and sine to work these out. So let's go ahead and do some side calculations. The cosine of pi over 2 plus theta is going to be the cosine of pi over 2 times the cosine of theta minus the sine of pi over 2 and the sine of theta. Now the cosine of pi over 2 is 0, so this just first term will be 0. The sine of pi over 2 is 1, so this is going to be the negative of the sine of theta. All right, now using our addition formula on the sine, this will be sine of pi over 2 cosine of theta plus sine of theta cosine of pi over 2. And we know that the sine of pi over 2 is 1. The cosine of theta will just be cosine of theta. And the cosine of pi over 2 is 0, so that term will drop out. So this is simply going to be cosine of theta. So this coordinate is going to be negative sine. And this coordinate, the second coordinate, will be cosine of theta. Okay, so that's a lot of work. We had to work a little harder to get r at E2, but r at E2 has components negative sine of theta, cosine of theta. And now these are going to form the columns of our transformation. So the rotation matrix is going to be given by the matrix with this as its first column, and this as its second column. We can call that matrix R of theta. That represents the transformation. And this is what we wanted to show. And so we can see that it's really just a matter of working with the unit circle and working out the coordinates of the transformations of E1 and E2 respectively. All right, so it's just a little bit of work with the unit circle. All right, let's head back to the class notes. In our next problem, I want us to study some simple projections. In each case, find the matrix associated with the given transformation from R2 to R2. First, P1 is a projection onto the x-axis, and second, P2 is a projection onto the y-axis. Let's go to the document camera and work out the matrices associated with each of these transformations. All right, welcome back. We're going to work out the matrices associated with a projection onto the x-axis and a projection onto the y-axis. Now, both of these projections are very simple. The input vector xy gets projected onto the x-axis, and so the output vector is simply going to be what I get when I take that second component and make it 0. So xy is going to get transformed into x0, and under P2, xy is going to get transformed into 0y. So both of these are very simple. They follow very simple formulas. P1 of xy equals x0, and P2 of xy equals 0y. Okay, now that we have our transformation rules, let's work out, let's say, a matrix A1 associated with P1, and we'll work out a matrix A2 associated with this transformation P2. So all we have to do is see what P1 does to E1 and to E2. So P1 at E1 is P1 applied to the vector 1, 1, 0, and that's simply going to be 1, 0. P1 applied to E2 is P1 applied to 0, 1. That's going to keep the first component, but 0 out the second component, so that's going to go to the vector 0, 0. So the matrix associated with P1 is going to have these columns, and so let's call it A1. It's going to have columns 1, 0, and 0, 0. Okay, there's the matrix associated with P1. Now we have to go through a similar exercise here for P2. P2 at E1 is P2 at 1, 0. Now the transformation rule says zero out the x-coordinate, keep the y-coordinate. So this becomes 0, 0. P2 at E2. So the rule is to zero out the first component, but it's already 0, so that's unchanged. And then we just keep the second component, so this is just 1. And so the matrix associated with P2 is going to have these columns. Okay, so we have fairly simple matrices associated with P1 and P2. It looks like we take the identity matrix and either lop off this component, this entry, make it a 0, or we lop off this entry and make it a 0. Okay? So together, A1 plus A2 is equal to the identity matrix. We're just lopping off different parts of the diagonal on the identity matrix. So there's the matrices associated with these simple projections onto either the x-axis or the y-axis. Let's head back to the class notes. Let's work out one last example. Let V be the vector with components 3/5 and 4/5. Find the matrix associated with the transformation T of U is equal to the projection of the vector U onto the vector V. Let's go to the document camera and work out the matrix associated with this transformation. All right, welcome to the document camera. We're going to find the matrix associated with this linear transformation from R2 into R2. So we've got an explicit vector V with components 3/5 and 4/5, and we're forming the projection of a vector U onto V. Now in principle, we know what to do. We simply compute U dot V over V dot V, and that's going to be a scalar that multiplies the vector V. Now, I've already done some work here. V dot V is just 3/5 squared plus 4/5 squared, and that's just equal to 1. And so this formula for T of U, this projection, simplifies. I just have to take U, dot it with the vector V, and then scale. That's going to be the scaling of the vector 3/5, 4/5. Now, to get the matrix associated with T, I have to carry out two calculations. I'll need to know what does T do to the vector E1. So what happens when I take T and apply it to the vector with components 1 and 0? Now, according to my rule, I have to take this vector 1, 0 and dot it with that vector V. And that's going to give us 3/5 plus 0. So this will be 3/5 of 3/5 and 4/5. Those are my components of V. And so that's going to be 9/25 and 12/25. Which I should really think of as a column. When I want to insert this into the matrix, it'll be helpful to think of this as a column that's being output. So T of E1 corresponds to the output vector 9/25 and 12/25. Let's do T of E2. That's going to be T applied to 0, 1. When I apply the dot product, I'm going to get 0 and 4/5. So this will be 4/5, scaling the vector 3/5 and 4/5. And so this will look like 12/25 and 16/25. And again, that should be, for the purposes of creating the matrix, it's better to think of this as a column vector. All right. So the matrix associated with T, we'll call it A, has columns 9/25, 12/25, and 12/25, and 16/25. And so what we're saying is that if I want to calculate T at a generic vector U, I simply take my matrix A and I multiply by the corresponding vector U. And that's going to have the effect of projecting the vector U onto this vector V with components 3/5 and 4/5. So we can represent this transformation by simple matrix multiplication. All right, let's head back to the class notes. Now, as we come to a close on this first part of section 3.6, one of the important things we learned is that a linear transformation can be represented by a matrix. And someone has developed a nice tool for visualizing transformations from R2 into R2 simply by specifying the corresponding 2x2 matrix. Now, what we can do is we can see the effect of, for example, the transformation associated with this matrix. We can click Show Pointer Vector. And this will be easier to do with my trackpad if I can go to full screen. What this allows us to do is manipulate our input vector and see the corresponding effect through this transformation on the output vector. All right, now all I want to do is take a couple of the examples that we've looked at and look at their corresponding visualizations. So we have, for example, this transformation, which corresponds to a reflection. Okay, we can see that this is the reflection through the x-axis. As I change this vector, as I manipulate this input vector, it's going to have give me the reflection of that vector through the x-axis. Okay, it's just mirroring my input vector through the x-axis. And if I change the roles of the 1 and the -1, it's going to give me a reflection through the y-axis. So now we can see mirroring through the y-axis. So as I change my input vector, I'm always going to get the mirror of that input vector through the y-axis. Okay. Another example we looked at was a rotation matrix. So let me do a counterclockwise rotation by 30 degrees. So when we compute the cosines and the sines at 30 degrees, we're going to get 0.866, a 0.5. I should have a negative 0.5 in this position, and a 0.866. And there's the corresponding rotation by 30 degrees. So as I change my input vector, I should see my output vector is always 30 degrees ahead in this counterclockwise direction. It might be a little easier to see if I impose the unit circle here. So if my input vector stays on the unit circle, my output vector should also be on the unit circle, but 30 degrees ahead, so to speak. All right, so it's always going to be a little bit ahead as I race around this unit circle. So that's our rotation matrix. Now, the last example I want to look at corresponds to the last example we computed. This was projection of the vector onto the vector 3/5, 4/5. All right, that's going to essentially give us projection of a vector onto the line through the origin with direction vector 3/5 and 4/5. Now, we can edit the components here. We're going to have a 0.36, a 0.48. This corresponds to those fractions that we calculated. A 0.48. And finally, a 0.64. Okay, let me get rid of the unit circle. And now what we're going to see as we scroll around is we'll see that our output vector is constrained. It's always going to be staying on that fixed, it's going to always be parallel to that fixed direction vector of 3/5 and 4/5. So no matter where I scroll around, I'm basically going to have my output vector sitting on that line. And as I move into different positions, I can sense the projection of this input vector onto that line or onto that direction vector. And we can see that very nicely represented here with this visualization tool. So I would encourage you to, and we'll do this in class, we'll look at we'll create some transformations and we'll look at their visualizations using this tool. So I thought I would show that to you. Now, this brings a close to the first part of section 3.6. So I will see you again for the second half when we take up the topics and complete the rest of section 3.6. So until then, take care and bye-bye.